All right, so what did you guys notice as similarities or differences? Let's just kind of popcorn them all out. Anything you noticed, you could just kind of call
For the bond energies on the left side, the H reaction is a lot, like the arrow is a lot smaller than the one on the right.
This arrow is a lot smaller than this arrow. Yeah, but interestingly, what does each arrow represent?
Bond breaking.
Yeah.
It's the difference between reactants and products. The difference between reactants and products. So it's the enthalpy of the reaction or the heat exchange from this reaction. And notice, even though this arrow is smaller, it's still representing negative 800 kilojoules. This arrow is big, but it's representing negative 803 kilojoules. So what does that mean about the scales? Are these being graphed on the same scale?
No.
No. So that's the first really interesting thing to notice, is that the scales are different. And that's in part because what's counting as the zero for potential energy is different when you're using bond energies versus enthalpies of formation. What did we say the zero potential energy was for bond energies? What counts as zero?
When they're atoms.
When they're totally
separated.
Separated atoms. And why? That meant no attraction. If they're totally separated, there's no attraction, so we're defining that as zero potential energy. So the zero for potential energy are defined differently. Okay, if you're talking about bond energies, the scale is set for potential energy equals zero if you just have separated atoms, right? So C, 4 H's, that's how we're representing atoms. What is the zero? How would you define what's going on here with the enthalpies of formation?
Those are elements.
And how did you know that?
It's on their state. Carbon is in solid, hydrogen is in gas, and then oxygen is in gas as well.
Yeah, so the state really gives you a clue. This isn't a carbon atom, this is carbon solid. So we're looking at a network covalent substance. This is an H atom, this is hydrogen as a molecule. And this is an oxygen atom, this is oxygen as a molecule. So these are elements. Okay, so for enthalpies of formation, the potential energy equals zero for elements. Okay, and the phase kind of helps you. So not carbon atom, but carbon solid. Not hydrogen atom, but hydrogen gas. So that's a big deal, noticing the different scale. What else did you guys notice as different or similar between these?
The heat of reaction is slightly different, the delta H.
That's true. It's mostly the same, but when you use enthalpies of formation, you get a slightly different value than you would for bond energies. We can talk about why. So this is the first thing, scales are different. Second thing you might notice is that the delta H of reactions are similar, but slightly different.
I have a question.
Yeah.
Is the orange arrow, I just want to make sure. The orange arrow is the H reaction, right?
That's right. So this difference here is a difference of negative 800 kilojoules. That's the delta H of reaction. And then if you were to calculate the same thing using enthalpies of formation, then you would get delta H of reaction to be negative 803. So they're only different by 3 kilojoules. And the reason for this is that it's more accurate to use enthalpy of formation data. I can just maybe put a small bullet point here. More accurate to use the delta H of formation, and that's because those values are measured directly by calorimetry. And calorimetry is a technique we're going to use in the next lab we do, which is called the Hess's Law lab. It's just a way to perform a reaction in an insulated thing like a styrofoam cup and measure heat differences. The bond energies though, so I can measure heats of formation directly because I can find carbon solid in nature. I can find hydrogen gas in nature. I can find oxygen gas in nature. So I could figure out, well, what is the difference between taking carbon solid and oxygen and hydrogen and making methane and oxygen? I could figure out or measure this. But I cannot find hydrogen atom in nature. I can't find this separated oxygen atom in nature. It doesn't exist because it's not stable. So bond energies turn out to be averages. They're not specific to each compound. So the second bullet kind of ran out of room is that bond energies, going to abbreviate BE, are average values. And that's great. Sometimes all we need is an average value to estimate how much heat is going to come out in a reaction. Sometimes we need to get more specific or find more precise ways of doing it. But both are useful methods. So overall, I'm going to zoom in a little here. When you look at these two methods, you're still starting from reactants. There's some positive number, some positive amount of energy it takes to go up to the zero of potential energy, be it atoms or elements, and then some energy released going to products, okay? And the total enthalpy of reaction, we said in the last lecture, for bond energies is taking the sum, that's what that sigma means, the sum of the enthalpy for bond breaking, that was this, which was a positive value, and then we said adding it to the sum of the enthalpies for bond making. And it was important to notice that even though all bond energies are written as positive values, energy comes out when you make bonds. So you always have to make this summation negative and this summation positive. when it comes to enthalpies of formation, it's really similar. The heat of reaction is going to equal summing up the delta H of formations for the reactants plus the sum of the delta H of formation for products I'll erase the time, that was just for me to keep track. And now when you think about the signs, look at these values. Negative 75, but it got turned into positive 75 because you were going up to 0. So enthalpies of formation tend to be negative, but you have to know that when you're adding up the enthalpies of formation for the reactants, you're going to have to take the negative value of them. So CH4 going to C and H2, well, if you looked it up in a table, you'd see negative 75, but you need to remember, oh, I'm going up, so positive 75. So it's the opposite, basically, for bond energies and heats of formation. You take the negative of this and take the positive of the products. And I looked in your book today. I highly suggest reading chapter 9, pages, I think 413 is where it starts in your textbook, to see how they explain using bond energies. And then chapter 6 is most of the thermochem, page 275. Start there to read about enthalpies of formation. But this is just kind of the big picture view for right now. Any questions before we move on? What we're about to do is compare, like, what do these values actually mean? What is an enthalpy of formation? You can also send me questions in the chat box if you don't want to publicly ask questions. Well, I'm going to move us on. Okay, so again, we're ultimately looking for the same thing. We're trying to calculate a heat of reaction. And 2 different energy scales can be used to estimate it. Okay, so we've already said we're using different scales here with different, with the potential energy defined differently for the 0. What I want you guys to do is just look at these values here for bond energies, and then look at these values here for enthalpies of formation. And if you could just kind of call out anything you notice, similar or different. Or any patterns that you see. There's actually a lot to notice in this table.
For the standard enthalpies of formation and the kilojoules per mole, it starts increasing as the bonding models, like attractions, like get really strong. Like graphite is a network covalent bond, and the other ones are like H2, O2, and those are very small. So I noticed that.
When you say small, you mean like they're negative, they're big negative numbers, so they're small?
Yeah. I was talking about the last one, enthalpies of formation, the last column.
Okay.
Yeah. Yeah.
Okay, yeah, like these are ionic too, and they have really, I'm gonna say big because I'm just looking at the magnitude. I'm noticing they're big negative numbers. And then, like you said, these are molecules over here and they're smaller. So that's kind of interesting. If the thing that you're noticing, Marissa, relates to attractions. So if you're going to form something ionic, it's going to have strong attractions, and so you're going to have a much, much lower potential energy. Because strong attractions mean low potential energy. You can also look at these graphs, because ultimately what we're trying to figure out is how are bond energies different from enthalpies of formation? And I gave you an example energy diagram you can look at. So maybe I'm going to send you into breakout rooms so that you can chat about this. I'm going to pause us again.